welcome you all. In this session, we are going to discuss the principle of DC link control. Outcome: after successful completion of the session, the student would able to explain the principle of DC link control. The major advantage of HVDC link is rapid controllability of transmitted power through a control of firing angle of the converters. Modern converter controls are not only fast but also very reliable, and they are used for protection against line and converter faults. The control of power in a DC link can be achieved through control of current or voltage. From minimization of loss considerations, we need to maintain constant voltage in the link and adjust the current to meet the required power. This is the basic diagram of DC link control. Here, EDR represents the rectifier voltage, RCR represents the rectifier resistance, RT represents the DC link resistance, and RCI represents the inverter resistance. Hence a minus is indicated, and here EDI represents the inverter voltage. So this is the voltage, VDI output voltage, VDR is the output of rectifier voltage, and ID is the current flowing through the DC link. So this is the basic schematic diagram of a DC link. So this link can be controlled, this DC link can be controlled either by controlling the rectifier station or by controlling the inverting station. So at any instant, one station will be acting as rectifier and another will be acting as inverter station. So consider the steady state equivalent circuit of two-terminal DC link. This is based on assumptions that all series connected bridges in both poles of converter station are identical. Usually, whenever you go for DC transmission, both the rectifying and the inverting station converters are identical. They are similar to each other and have same delay angles. Also, the number of series connected bridges NB in both stations are same. See, if say for example, if we are using 12 pulse converter at both the stations, then here the number of 6 pulse converter, that is 2 6 pulse converters, can be added up to form a 12 pulse converter in series, right? So if we are going for such cases, the same configuration must be there in the inverting station also. Under normal condition, the rectifier operates at constant current control and inverter operates at constant excitation angle control. The power reversal in link can take place by a reversal of DC voltage. This is done by increasing the delay angle of station initially operating as rectifier while reducing the delay angle of station initially operating as inverter. Thus, it is necessary to provide both extension angle control and the constant current control at both the terminals. The feedback control of power in DC link is not desirable because of two reasons. One is, at low DC voltage, the current required is excessive to maintain the required level of power. This can be counterproductive because of excessive requirements of reactive power, which depress voltage further. The constant power characteristic contributes to negative damping and degrades the dynamic stability.